So we have seen the cross flow and the parallel flow and how to calculate the log mean temperature difference. We have also seen that for special cases where the capacity of the hot side tends to infinity, for example, for the case of a condensing vapor, the temperature profile of the hot side fluid remains constant, whereas the cold side fluid it increases. Conversely, when the cold side fluid temperature has a very high capacity, in that case the cold fluid temperature will remain constant, whereas the hot fluid temperature decreases. So these two separate cases where CH is very large as compared to CC, or CC is very large as compared to CH, that we have seen how the profile look like. We have also seen how the two profiles would look like when CH is equal to CC, that is the capacity of the hot fluid is the same as that of the cold fluid, in which case the temperature profiles for the hot fluid and for the cold fluid, they will simply be parallel lines, straight parallel lines, where the delta T will remain constant throughout. Now, as I mentioned, that the heat exchangers can be multi-pass heat exchangers, or the heat exchangers could be such in which you are going to have cross flow across the tube bundles. So when you have a multi-pass heat exchanger, you may start with parallel flow, but in the second pass it's going to be counter flow and so on. And when in cross flow, the flow is not going to, you cannot say that it's parallel flow or counter flow, it's rather the flow is across the flow of the flow, whatever liquid that is flowing through the tube, and the shell side fluid is going across. So all these different types of flow which cannot be clubbed as purely counter flow or purely flow in the same direction are called as mixed flow. So what is to be done to LMTD in order to take into account the multi-pass heat exchangers, situations which are common in multi-pass heat exchangers and in cross flow heat exchangers? So what is done is a correction factor to LMTD has been introduced, which is commonly denoted by F. So by this factor F, the LMTD has to be corrected before you can use it in the relation Q is equal to UA delta T LM. So the revised formula for cross flow and for multi-pass heat exchangers would simply turn out to be Q to be UAF, the correction factor, multiplied by delta T LM, the log mean temperature. This factor F, the correction factor F, would depend on various things. It's going to depend on what is the temperature of the shell side, the temperature of the tube side, both for the hot fluid and the cold fluid, and the results for a large number of situations are expressed graphically, from which it would be possible for us to find out what is the value of F for a specific flow situation. So the correction factor F evaluated from the graph used in conjunction with LMTD will give us the corrected LMTD that can then be used in the relation Q is equal to UA delta T. So I am going to show you how this F varies with these parameters, and the graphs are available in your text. So whenever while designing heat exchangers, whenever you come across these kind of mixed flow situations, always look for the correct value of F to be used in the LMTD relation. So let's take a look at what we have over here. So for the case of correction, what we need to do is we need to correct delta T LM as F delta T LM based on pure counter flow. So this is important. You first calculate delta T LM as if the flow is taking place in counter flow. Okay. So you calculate delta T LM as if the flow is taking place in counter flow, multiply that with F in order to obtain delta T LM for the case of mixed flow. So this is for mixed flow conditions, this is for counter flow, and this F is the correction factor which is to be used for this. So, this is what we have is graphical representation of the factor F. It's going to look something like this. There will be a family of curves and this is the value of P is defined in this way, and the family of curves are for different values of R, which are Ti minus T0 by T0 minus Ti. So, this temperature T refers to the shell side temperature, and T refers to the tube side temperature, O for the inlet, I for the outlet. Okay. So, P, if you can see, P ranges, so this is from 0 to 1, P ranges from 0 to 1. Okay. So, this represents the thermal effectiveness. Of the tube side fluid, and R ranges from 0 to infinity. 0 corresponds to pure vapor. So, if it is a pure vapor, then you can see that T0 is going to be equal to Ti. So, it is a pure vapor, or it's a condensation on cell side, and infinity to evaporation on the tube side. So, when you read it carefully once, you would see the significances which are obvious based on how we have defined P and R. So, the important part here is you calculate what are the different temperatures, and then from the different temperatures you find out what is the value of F, and use that value of F to correct the log mean temperature difference that you would have obtained if it is pure counter flow. So, pure counter flow log mean temperature difference corrected by the factor F would give you the log mean temperature difference to be used in the relation Q is equal to U A delta T. So, that's all in that expression, and we are going to solve problems to show you how to use LMTD in real situations for actual practical problems, but we would do that in the next class. In the remaining time of this class, I am going to discuss about the simplest possible heat exchanger that you would come across, which is a double pipe heat exchanger. So, I will talk about the description and the design considerations of a double pipe heat exchanger, and then once that is over, then we are going to solve, there will be a tutorial class where we are going to solve problems on LMTD and problems on double pipe heat exchanger before we move on to the design of shell and tube heat exchangers. So what is a double pipe heat exchanger? A double pipe heat exchanger consists of two concentric tubes of different diameter. So there would be the tube, inside tube is going to be circular in cross section, whereas the space between the inside tube and the outside tube is going to be annular in nature. So there would be flow through the tube and flow through the annular space, maybe in the same direction, maybe in opposite direction, that is in parallel flow or in counter flow. And these tubes are going to be attached to the main pipe through certain glands, heads, and so on. Now, if you think of the design of these, they are the easiest to design. Okay, they are easy to fabricate. The only limitation is that it's going to be expensive if you want to have a double pipe heat exchanger that bends and comes back once again. So the tube, the fluid flows in one direction and comes back in the reverse direction, and you have annular flow in there. So whenever you have a bend like that, you are going to introduce pressure drops. The other limitation of double pipe heat exchanger is that it only provides small values of the available area for heat transfer. So the heat transfer area provided by a double pipe heat exchanger is generally small. So wherever you have a small duty heat transfer situation, you can prescribe double pipe heat exchanger. But the moment heat transfer area requirement increases, the double pipe heat exchanger will not be economical anymore. It is also difficult to clean the double pipe heat exchanger, to get rid of the deposits, the dirt, and that would deposit on the inside and the outside of the tube during elongated periods, extended periods of action. Finally, the double pipe heat exchanger is limited by the length. You do not get too long a pipe to make a double pipe heat exchanger. So double pipe heat exchangers are generally of the side of 12 feet, 20 feet, 25 feet at the most, and those are going to be used for fabricating a double pipe heat exchanger. So double pipe heat exchangers will only be cost effective if your heat duty is small. And you also have to think, another disadvantage of double pipe heat exchanger is that it requires a large space as compared to a shell and tube heat exchanger, which is much more compact. So space comes at a premium. So therefore, use of double pipe heat exchanger is not justified unless the heat load requirement is small and you have enough space to accommodate a double pipe heat exchanger. However, they are the simplest one to fabricate, simplest type of heat exchangers to analyze. So we'll quickly go through, and they are used in industry at a number of places, number of situations. So we need to know what is double pipe. We'll quickly go through the double pipe, their design issues, and some of the calculations, and then move on to shell and tube. So let's first draw a picture of the double pipe heat exchangers. As I said, the length could be between 12, 15 and 20 feet. So, this is what a double pipe heat exchanger would look like. The one that you see in the green is the inside tube, this is the outside tube, and this is the inner area through which the liquid flows. So, the double pipes are connected to the base by glands. Okay, so, this is one gland, this is another gland, and you have a T junction here, which is where the fluid is going to come, which is going to flow through the so the hot fluid, or let us say the shell side fluid, is going to come through this. The shell side is going to flow in this direction, and then it is going to be collected at the other end. So, they are not mixed with what is happening inside the tube side fluid. And the tube side fluid, it is a counter, let us assume it is a counter flow heat exchanger. It is going to move in this direction and to outside. So, this is what the simplest heat exchanger that you can think of, but it is only used if area required for heat transfer is small, of the order of 100 to 200 feet square. That is the area which is required. And the coefficients, the film coefficients, that means the HI or HO, can be calculated if it is a laminar flow. Then the Sieder-Tate correlation, that is Nusselt number based on diameter is 1.86, Reynolds based on diameter times Prandtl to the power L by D. We now know what these equations look like, mu by mu s to the power 0.14, and if it is turbulent, I am not going to use, I am going to, so it is going to be Dittus-Boelter equation, Dittus-Boelter correlation for Sieder-Tate, and we understand that Sieder-Tate equation is to be used when you have large property variation. So, when the temperature of the tube, at that temperature of the tube, if your viscosity varies significantly, then you are going to use Sieder-Tate relation, otherwise you use the Dittus-Boelter equation that we have described before, that we have, but for completeness I am going to include it here as well, where the Nusselt number is 0.023, Reynolds to the power 4 by 5 and Prandtl to the power n, and this n can be 4 if Ts is greater than Tm, and n can be 3 if your Ts is less than Tm. And for the case of Sieder-Tate, the Nusselt number is simply going to be 0 to 7 Reynolds to the power 4 by 5 times Prandtl to the power 1 by 3, and the viscosity correction factor mu by mu s to the power 0.14. This is 1 by n. Okay. So, this is when you have a significant variation in the case of in the case when you have a significant variation in the property. But whatever I have described here, they refer to flow inside the tube. So, what is to be done when you have flow in the annuli? The common practice for that is you find out what is the hydraulic diameter for the annuli, and then use all these equations depending on whether you have laminar flow, you have turbulent flow, you have significant variation in property. In all those correlations are equally applicable for the case of annuli as well, provided you replace the diameter by the hydraulic diameter. Then all these relations can be used. So, to in order to find the for the keys for the annuli, you find out the hydraulic diameter, which is d suffix h and is defined as 4 AC by P. So, AC is the cross sectional area for flow of the liquid and P is the weighted perimeter. So, this P is the weighted perimeter of the annular region and AC is the cross sectional area which is available for flow. So, dH is therefore 4 times pi by 4 d0 minus di square, and obviously the weighted perimeter would simply be pi d0 plus di. So, this would give rise to d0 minus di. So, for turbulent flow, therefore, this can be used in terms of by simply replacing dH with the d with di in Reynolds number. So, in Reynolds number, replace d with the hydraulic diameter for the annular region. Okay. And you take care of the fouling factors as before. When you have fouling present in this, 1 by ud is 1 by uc plus rd, the fouling factor at the inside plus rd of the outside. So, this is the clean coefficient which depends on HO and HI. This is the coefficient while the double pipe heat exchanger is in operation. It is sometimes called as the design or overall coefficient. So, this is the design or the overall coefficient and this is the clean coefficient, and these two together are sometimes replaced by sometimes expressed as RD, where RD is the dart factor. So, this dart factor, the clean coefficient, together they could give us the overall coefficient which is to be used for all our design purposes. And one more thing that we need to keep in mind is this the clean overall coefficient is simply 1 by HO plus 1 by HO plus 1 by HI, and the heat transfer coefficient on the this is simply going to be, that's directly from geometry, and it is HI times ID by OD. And finally, what you get once you get all these, you are going to get Q is equal to UD A delta T. Now, remember that in the case of double pipe heat exchangers, there is no need to calculate the correction factor F for LMTD, because for double pipe heat exchangers it is either purely counter flow or purely parallel flow. There is no question of mixed flow for the case of double pipe heat exchangers. So, the only thing which remains right now is to express the pressure drop, or to calculate the pressure drop and how it is related to the flow rate of the fluid flowing in the annulus as well as flowing in the tube. When it is flowing in the tube, we know how to calculate the pressure drop. So, the same equation, the same value of friction factor that we have obtained, the Brescia's friction factor or the friction factor which we have obtained from the Moody diagram, can be used for the tube, and the same can be used for the annular region as well, if we replace the diameter to calculate the Reynolds number with the hydraulic diameter of the system. So, the pressure drops are generally calculated using the standard relation of delta P that we have used for the case of Moody diagram, the friction factor that we have obtained from the Moody diagram. So, I will simply write those expressions for you, but it should be, it is already known in your known to you. So, the pressure drop in pipe and annuli can simply be obtained if it's F equals 16 by RE, if it is laminar, if it is turbulent, it is 0.014 plus. All these relations are known to you. So, this is from, so this is for the case of laminar flow, this is for the case of turbulent flow. You can use either this correlation or you can simply use Moody diagram. Okay. And for annuli, so this is for the tube or pipe. For annuli, replace D by D E prime, that is the effective diameter, to obtain the friction factor F. So, this is the hydraulic or equivalent diameter that we have obtained, and delta P would simply be equals 4 F G square L by 2 G rho square D E prime, where G is simply the mass velocity. So, G is defined as the mass velocity. Okay. And generally a delta P of 5 to 10 psi is provided in double pipes. So, to once again to calculate the pressure drop, we can use the same relations that we have used for calculating the pressure drop in a pipe. For the case of annuli, we replace the diameter by the hydraulic diameter, use the same relations. In the pressure drop, it can be expressed the standard formula that we have done in terms of the velocity, or it can be expressed in terms of the mass velocity. And you would see later on that the heat transfer coefficient, when you use the relations, the heat transfer coefficient is going to be proportional to G to the power something, I think G to the power 0.8. So, when you increase the value of G, the mass velocity of the fluid flowing through the tube or through the annulus, you are simply going to increase H. But when you look at the pressure drop calculations, the pressure drop calculation increases with G in as G square. So, an increase in H with G will be compensated by the requirement of higher pressure. So, there is an economic decision which has to be made on how much of pressure drop you can sustain, you can provide, and what is the enhancement in terms of the energy transfer that you are getting out in the process. So, it's an engineering calculation based on the cost estimates which one has to perform to decide what is the flow rate to be used in a double pipe heat exchanger. The customary is to provide about 5 to 10 psi pressure drop, allow that much of pressure drop for flow in a double pipe. Now, whenever you have some entry point, at the entry point there would be some losses, at the exit there would be some losses, and if you are going to provide a bend at the end, so that it's going to look like an U-tube heat exchanger instead of a double pipe heat exchanger, you are going to add some more pressure drop. So, all these calculations are required in order to make a judicious decision in the design of a double pipe heat exchanger, which is easy to fabricate, expensive to maintain, only economical if the area requirement is small, and if you do not have any problem of space, because these double pipe heat exchangers, they take up a significant amount of space if you compare that with the heat transfer area provided by them. So for all practical cases, wherever you have a high surface area transfer area requirement and you do not have enough space to put a bulky double pipe heat exchanger, one should always go for shell and tube heat exchanger, which we are going to discuss in the next class.